Hi everyone. Today we are diving into eutectic alloys, why they are important, how to interpret phase diagrams, calculate phase compositions, and weight fractions for the primary and eutectic phases in hypoeutectic, eutectic, and hypereutectic alloys, and how all these affect macrostructures and mechanical properties. If you remember in previous video, we unlocked the secrets of the material science with mastering phase diagram, lever rule, phase fractions, weight percents, and their relations to mechanical strand breaking down binary alloy like copper nickel and SBBI step by step. Eutectic alloys are so crucial in applications such as soldering, casting, designing alloys with precise melting points and strong uniform macrostructure. So understanding eutectic compositions allows engineers to achieve enhanced strength, hardness, reliability in industrial and structural material. Okay. Why eutectic systems are important? Eutectic systems are so crucial because they define the specific compositions and the temperatures at which liquid phase simultaneously transform into two solid phases. This point, known as eutectic point, if I want to show you in this phase diagram, here is the eutectic point. Above that, we have liquid phase, and below that, we have alpha plus beta, that both of them are solid. So this point, known as the eutectic point, represent the lowest melting temperature for the mixture and ensure that all these phases coexist in equilibrium. What's the meaning of low melting temperature? For example, for changing to liquid, if the composition be different, for example, if be here, the melting temperature should be at this temperature. So it is the minimum melting temperature, means exactly at this composition or C naught, will reach from the solid to liquid at this temperature, that for different alloys, eutectic specifications, temperatures, composition, and some things are different. So eutectic solidification produce fine uniform macrostructures that enhance mechanical properties. Means if we be here at eutectic, and we have the macrostructures at this composition percent and temperatures, we have the macrostructure that reach us to the best mechanical properties and provides predictable phase behavior and allows engineer to design alloys with reliable and consistent performance. Understanding this concept is key to controlling material properties in industrial and structural application. Okay, binary eutectic systems. What's the meaning of binary? If you remember from previous video, binary means we have two components. But at eutectic systems, we have three single phase region. The first one, liquid, that you see as green color here. And means we are talking about this liquid. And alpha phase, that here is the alpha phase. Here we have the beta phase. They are single. Each solid phase has a limited solubility in the other. For example, with alpha, mostly composed of one component, and beta mostly of the other. At the eutectic temperature, what is the eutectic temperature? For example, for this alloy, that is the copper and silver, or Ag, CuAg, the eutectic temperature means the temperature related this point is 779 centigrade. So at the eutectic temperature, or TE, the liquid phase disappear. What's the meaning? Means above that we have liquid, little below that 779 for this alloy, liquid 100% disappear and convert to solid phases. And the eutectic compositions, or CE, is the composition or corresponding to mixture with the minimum melting temperature. These fundamentals are essential for understanding phase transformations and predicting how alloys solidify. In this graph that you see, CuAg, alpha phase is mostly Cu. What's the meaning of that? If you look at this corner and read the C% or composition weight percent of that, it should be about 8, yeah? So 8%. We have the Ag, and 92% we have Cu. So in the CuAg, alpha phase is mostly Cu, but a limited amount of Ag can dissolve in it, about 8% of the at the eutectic temperature. The beta phase, as you see here, shown by the orange color, the phase is mostly Ag. If you look at here, the minimum Ag is 91.2 and reach to 100%. So the beta phase is mostly Ag with a small amount of Cu soluble in it. The rest of the alloy cannot dissolve in the phase and form other solid phase. At the eutectic temperatures, means 779, liquid with 71.9 weight% Ag transform directly to alpha and beta phases as a solid phases directly. And as you know, alpha is most part of that is Cu, and for beta, most part of that is Ag. Okay. Here, the eutectic transformation. The eutectic reactions occurs when a liquid at the eutectic composition solidifies into solid phases simultaneously. Means that if we have liquid and in these directions, means what happens means cooling. Convert that to alpha and beta and change the color. And if we heating, means melting, we have alpha and beta, and this E means eutectic, alpha eutectic and beta eutectic convert to liquid. So at this point, the system is invariant, meaning the temperatures and composition are fixed, means TE fixed, CE fixed. T is the temperatures of eutectic, and C the composition at eutectic. These transformation lead also distinct macrostructures where both solid phase coexist, means we have alpha, beta simultaneously, forming the basic for many practical applications due to its unique mechanical and thermal characteristics. The eutectic point is a special point on the binary phase diagram. Temperature is the lowest melting temperature, TE, for the alloy system, and composition means eutectic composition, or CE, for different alloys different. For example, for copper, silver, CuAg is 71.9 weight% Ag. Phases in equilibrium in eutectic point, 3 phase coexist, liquid, alpha, and beta. Example. In this slide, we want to talk about how to calculate the phase present, their compositions, and relative amount using the lever rule. For 40 weight percent SN, 60 weight percent PB alloy at 150 centigrade. Determine the phase present. Okay, so if you remember from the last video, with this weight percent and the temperatures, we show that where we are. We are in, it is the temperature is below that eutectic temperature. So definitely we are in solid phase, and we have alpha and beta. So here is alpha and beta phase. Okay. If we want to find how much alpha we have, how much beta we have, it is the tie line, okay? Intersect alpha region at this point and read the composition weight percent of this point, that is 11. So C alpha is 11 weight percent SN. As the summations, we have two alpha and beta, two phases. So the summation should be 100. Then the other one, for example, should be the difference between them. Okay, and it intersect beta at this one. Read the C of that, it should be 99, okay? So we are in alpha plus beta, the composition weight percent of SN in alpha is 11%, and the composition weight percent of SN in beta is 99. But how much weight fractions of alpha and beta that the summation should be, the summations of both of them should be 100. Okay. We use lever rule or rule 3 from the last video, if you remember. Okay. For the alpha or W alpha, which side is far from that is S per the total S plus R. What is S? It is 99 minus 40, the composition related this point, okay? And the total 99 minus 11. So we have 16, so W alpha is 69.7%, yeah? In this 69.7%, how much we have SN? We have 11% SN, and how much? 89% we have PB. Okay. For W beta, we can say 100% minus W alpha, or vice versa. We say which side is far from the beta is the R divided by total. It should be 33. So we can say W, or weight fractions of beta phase, we are in two phases, alpha plus beta. From this, approximately 70% for alpha, 33%, yeah, and 33% for beta, yeah? And for this beta, how much SN we have? 99% SN and 1% PB, okay. Here we have another examples. Here we have 40 weight percent SN and 60 as same as before, but the temperature is 220. What's the meaning? It means a little higher, not a little, because TE is 183, the temperature is 220. If we show the point, we are in this point. In this point, above the eutectic temperature, we are in phase of liquid plus alpha. So the answer for the phase is liquid plus alpha. We use rule 2. What's the meaning of rule 2? Tie line intersect alpha and liquid. Read the C of the alpha should be 17 weight percent SN. How much PB? 100 minus this. It should be 83% PB, okay? and intersect the liquid at this point with that 46% SN, and it should be 54% PB. But how much weight fractions of the alpha and weight fractions of the N? For weight fractions, we use a lever rule. Okay, which side far from the alpha? S. Divide per total R plus S. S, R plus S. Substitute here 21%, and for liquid 100 minus 679. What's the meaning? Means we have 21% alpha because we have two phases simultaneously, liquid and alpha. 21% alpha, but in this 21%, how much percent? 17% is SN, and 83% is PB. Okay, and how much weight fractions of the beta? We have 79%, and for this 79%, we have how much SN? We have 46% SN and 54% PB. Okay, hope everything be clear for you. Macrostructure. Macrostructure development for low SN alloy. What's the meaning? That if you look at the alpha region, the minimum composition and weight percent is 2% at here, and the maximum only alpha, it should be 18 point something. So for alloys with very low SN, means content means lower than 2%, the macrostructure as room temperatures is entirely alpha, means we are talking about less than this at low temperatures. Okay, it means entirely is alpha phase. Polycrystallines with uniform grain composition, as you see here at the dark blue, is completely alpha. Yeah, so polycrystalline with uniform grain compositions, we have no other phase are present, creating predictable mechanical behavior. This illustrates how overall compositions affect final macrostructures in hypoeutectic. What's the meaning of hypoeutectic? Means before eutectic, yeah? Here, we are talking about between 2% and 80%, means we are talking about this part, yeah? In alloy with slightly higher SN content, means we have alpha grains form first, followed by a small beta phase particle desired and dispersed around them. What's the meaning of that? Okay, look at this dashed line, yeah? Here, if I show you by green color, here we are 100% liquid. When we reach here, we have some green as the alpha that you see as a dark blue here. Cooling, we reach to 100% alpha, and you see that is completely isomorphous and polycrystalline with 100% alpha. Then cooling more than that, we reach to alpha plus beta. This alpha plus beta means we have another particles of the beta that dispersed in alpha. And here we talk about that hypoeutectic, means before eutectic point. So we have polycrystallines with alpha grain and a small beta phase particles that disperse in them. So understanding this evolution allows precise control over material property during the cooling process. Okay. Another, this is the eutectic point, means above that temperatures, we have 100 liquid 100% liquid, and below that we have 100% solid. But solid, we have two phases, alpha and beta. At the eutectic composition, solidification produces a lamellar structures, means layer by layer. If you I zoom here and see the layers, the blue layers, for example, are alpha, and the red layers is the beta, and lamellar layers or eutectic macrostructures. But if we are talking about some things here, except lamellar, we have some grain. Means we have this lamellar plus some primary that you see in next slide too. So here we don't have any primary at the eutectic point or eutectic temperatures and eutectic composition weight percent. We don't have any primary, not alpha, not beta. The only thing that we have eutectic macrostructures or lamellar structures, means layer alpha, layer beta. This is so fine, uniform macrostructures, enhanced mechanical performance and properties include strength, toughness. So it is the reason that we as designers and engineers looking for the eutectic point, means fix and control the weight percent as or composition percent at this composition or CE and temperature at this for reaching to best macrostructures, uniform, and best mechanical performance. Okay. Lamellar eutectic structures, visualizations, microconstituents. This slide illustrates the lamellar eutectic macrostructure resulting from the solidification slightly above the eutectic temperature. For example, we say that if the SN weight percent should be between this point, 18.3, and this point, or this C, or weight percent SN, means if we be in this region, what's the meaning? Means we have alpha plus beta. But for alpha, we have two structures. One of them is eutectic alpha, another we have primary alpha. Primary alpha means comes from this dark blue grains, yeah? Means bigger than that. We have primary alpha, and you see here, if I zoom here, you can see that this dark blue circular, it is primary alpha, yeah, and these layers are eutectic macrostructures. So it is primary alpha. Here you see this dark blue, and this one, it is the eutectic alpha layer, and we have another layer as a red one or purple one, and it is eutectic beta. Okay. For example, it is an example that the temperatures is approximately near the TE, we consider that, and we draw a horizontal line, intersect the alpha region as 18.3, so C alpha is 18.3, intersect the liquid region as 61 point, means this 61.9 weight percent SN. So how much we have alpha? how much we have L, because we have a little above the eutectic temperatures. For alpha, which side is far from that is S plus R plus F is 58%, and for liquid is 50% liquid too. So just above TE, C alpha is 18.3 weight% SN. And if you continue that, C beta should be 97.8% SN, and W alpha equals S per R plus S 73%, and beta is just, so it is a little below, just below, sorry, T. So above TE, we have L plus alpha, means this region, yeah? So C alpha is 18.3, C liquid is 61.9, alpha is S plus R 50%, and liquid is 52. What's the meaning of that? Means above TE for temperatures of eutectic, we have W alpha is 50 weight%. From this 50, 18.3 is SN, and 100 minus 18.3 is PB. Okay, and W liquid is 50% again, and here 61.9% SN, and 100 minus 61.9 is PB. For a little below that, a little below that means we are talking about a little below. That means we are in alpha plus beta below. So C alpha is 18.3, and W alpha is 73%. 73% alpha, 18.3% SN, 100 minus 18.3% is PB. Another phase that we have is 27% phase beta, and this phase beta we have 97.8 SN, 100 minus 97.8 PB. Okay. Another examples. We have 30% SN, 70% PB alloy at 1820, means a little below that, which point, which temperatures, below the temperatures of eutectic. Eutectic 183, 30% SN means we are in dashed line. In which region we are? We are in alpha plus beta. But right side or left side? We are left side of the eutectic. So we consider this as hypoeutectic, and we cool that, means we expect that here we should have a primary alpha, eutectic alpha, and eutectic beta. So we have two phases for solid, but alpha has two macrostructures, one of them primary, one of them eutectic alpha. But for beta only we have eutectic beta. Okay, you see the tie line. Tie line intersect the alpha as 18.3, beta as 97.3 SN. So for alpha, 18.3% SN, 100 minus that is 81.7 PB. For beta, 97.8 SN, 100 minus that should be 2.2 PB. Amount of the alpha or weight fractions of the alpha, if you remember, means the side far from that means 97.8 minus 30 divided by total. It is alpha, but it is beta, but not finished. Why? Because this alpha is alpha primary plus alpha eutectic. Both of them is 85.3. If I want to find how much alpha primary and how much alpha eutectic, we should analyze that you see next slide between alpha region, means this region, and eutectic macrostructure. Okay, here. So if you remember, we found alpha, but how much is primary alpha? Again, it is another tie line between alpha and eutectic, and we are at this point, yeah, 38%. For primary alpha, it is primary alpha because of this region is primary alpha. Which side far from primary? This side. Should be 61.90 minus 30 per the total. So it is primary alpha. If you remember, so we found that the total should be 100. Beta, we have only one beta, that is eutectic. So the fraction weight that we found here for beta not change, 14.7, okay? So 100 minus 14.7 and 73.2, that is primary alpha. So it is alpha primary. It should be alpha eutectic. So the amount of the primary alpha, 73.2 primary, 12.1 eutectic, and beta, 14.7 is eutectic beta 2. In this slide, you see the lamellar macrostructure. The eutectic composition solidify into lamellar macrostructures, where alternating layers of alpha and beta phase form. These arrangements correspond directly to a phase fractions calculated previously. Primary alpha, eutectic alpha, and eutectic beta. Yeah. Define uniform lamellar enhanced mechanical properties such as strength, toughness, and thermal properties. And it is the reason that we are looking for eutectic reactions, means reach exactly to that temperature, TE, and exactly that composition percent CE for reaching to lamellar macrostructures for the best performance or mechanical property. So visualizations, the macrostructures help us that connect phase diagram calculations with practical material properties, showing how eutectic system produce a predictable and useful solidified structure. Okay, we talked about hypereutectic and hypereutectic before, but again, if I want to summarize and review so fast, at the dash line, it is the compositions of the eutectic. Means here, we only have lamellar macrostructure, exactly at this composition rate, okay? But at the left side of that, we have primary alpha plus lamellar. So this layer by layer is alpha plus beta, one layer alpha, one layer beta. But these circular or particle parts here, as you see, wrote alpha, means they are primary alpha. Yeah, but at the right side of that, these layers are eutectic structures or macrostructures or lamellar macrostructures. But these grains, you see primary beta. So at the right side, we say hypereutectic, and at the left side, before reaching to composition weight percent or CE, we say hypoeutectic. Okay. Eutectic alloys are crucial because they solidify simultaneously in two solid phases at the lowest melting temperature and producing a fine and uniform macrostructure. These macrostructures enhances mechanical properties such as strength, hardness, wear resistance, while allowing predictable phase fractions through the level. Some common binary eutectic alloys, such as PBSN, that use for electronic soldering, which provides a sharp melting point and a strong corrosion resistant joints. Another popular eutectic alloy, it is AGPB or silver lead, that used for bearings and electrical contacts, offering high wear resistance and good conductivity. Another popular eutectic alloy, PBSB, for lead acid battery grids, providing the hardness and corrosion resistance. And the next one is SNAGCU, that's the lead-free soldiers and delivering a precise melting and fine microstructure. And the other one is COAG system, that this alloy or copper silver is used in thermal and electrical component and offering high strength and excellent conductivity. And overall, controlling eutectic compositions allows engineers and us to design alloys with the tailored melting points and optimized mechanical properties. This ensures that the components meet the operational and structural requirements that we are looking for, that and be a more reliable structure. Okay, thanks for watching this video. If you enjoy it, please don't forget to like, comment, and subscribe to our channel. We have a series of interesting upcoming videos, include iron carbon alloys, iron carbide phase transformations, cooling transformation, and phase diagrams, which are essential for understanding the steel and cast irons or the material understanding. Stay tuned for more insights into material science and mechanical engineering. Thank you so much, and bye-bye.